So now we'll take a look at some harder examples of simultaneous equations. You can solve these however you would like. The general process of solving them is going to work the same as the basic examples did. They're just much harder. The forms of the questions are much harder and the answers are harder. Because of this, when we're doing them, I would recommend rounding them to a certain number of decimal places. We might say um, 2 decimal places and checking them with those decimal place rounding values. So I'm going to throw you straight in. So have a go. Good luck. Pause the video now and give them a go. Okay, so now that you've done these, let's go through them. So I'm going to give myself quite a lot of room to work on question 1. So let me move question 2 down there. So we have a plus b equals 8 and a squared plus ab plus b squared equals 50. These equations are a little bit messy. They have lots of stuff floating around. What we might try and do is we might try and rearrange this one for b and then plug it in to equation 2. So we might use substitution. So if we minus a from both sides, this gives us b is 8 minus a. Now this is important. We'll come back to this to find the other b value. But we're also going to plug 8 minus a in where the b's are. So here and here. So equation 2 becomes a squared plus a times 8 minus a plus 8 minus a squared is equal to 50. Let's expand this whole thing. So we have a squared plus a times 8 is 8a. A times minus a is minus a squared. We then have an 8 minus a all squared, so that's plus 64 minus 8 times a is 8a. 2 of that is 16a, and then minus a times minus a is plus a squared equals 50. So we have a plus a squared, a minus a squared. We can minus 50 from both sides, and this is going to give us a squared, which is the a squared, the only a squared term. We will have plus 8a minus 16a, that's minus 8a. Then we have 64 minus 50, that's plus 14. This equals 0. So this simultaneous equation reduced to a quadratic. Now we want to solve this quadratic, and it's going to give us the a value, or if there are two a values, it's going to give us both of those a values. So roots 1 and 2 of the quadratic. The coefficient of the a squared is 1, coefficient of the a is minus 8, the coefficient of the numeric term is 14, so we get 8 plus minus the square root of minus 8 squared, which is 64, minus 4 times a times c, that's 4 times 14, that will be minus 56 all over 2a, which is 2. So this is 8 plus minus the square root of 8 on 2. So we have found two a values that seem to satisfy this equation. We're going to decimal approximate them. So we're going to call them a1 and we're going to call them a2. So a1 will make the one with the positive square root. So we have 8 plus the square root of 8 on 2. That is equal to 5. That's 5.41 to 2 decimal places. And then a2 is this expression with the minus in front of the square root. That is 2.59 to 2 decimal places. Well, these are our two a values. Each of them have a corresponding b value. We know b is equal to 8 minus a, so we subtract these values from 8. 8 minus 5.41 is, so b1 ends up being 2.59. 2 decimal places. So this is one of our solutions. And then the other one is 8 minus 2.59. That ends up being B2 is 5.41 to 2 decimal places. And these are the solutions to this particular harder simultaneous equation. And you can check this by plugging them in, and you'll find it's true because the equations are in a sense symmetrical. So whatever value A had, the value that B that solved that, you could swap those and that would work as well. That's why A and the two sets of solutions are sort of the opposites of one another. Now, when you do your check, I'm not going to do the check here. I've already done the check on the computer before. I know that these are, in fact, the solutions. When you do your check, you're going to plug them back through into the equations, and you should get the sum of them is roughly 8, and then the other expression, the evaluation of that expression is roughly 50. If that's right for both of them, then that confirms your solutions are correct. And these ones indeed are. All right, so let's have a look at the next one. This one has a linear and then it has something that has a product of two terms. So what I might do is I might rearrange this one. I'm going to add 4 to both sides. This will give me AB is equal to 4. I'm going to divide both sides by, I suppose I'll divide both sides by A. Doesn't really matter which way we go, but we've got B is equal to 4 on A. Now, we're going to come back to this later once we've got our A value to give us our B value. We're going to substitute this B for 4 on A. So this makes equation 1, 2A minus 4 times 4 on A equals 10. Well, this is probably going to be a quadratic, so let's solve it. We'll multiply everything by A times A times A times A, cancels this A. We get 2A squared minus 4 times 4 is 16 is equal to 10A minus 10A from both sides. We get 2A squared minus 10A minus 16 equals 0. Divide everything by 2. And we get our reduced quadratic A squared minus 5A minus 8 is equal to 0. So now if we try monic factorizing this, two numbers that multiply to make 8 add to make 5, well, it's either going to be 4 and 2, 1 and 8, or something like that. That doesn't really seem to work. So we will use quadratic formula to solve this. So the coefficient of the squared is 1. The coefficient of the linear is minus 5. The coefficient of the numeric term is minus 8. So we find roots 1 and 2 are minus minus 5, which is 5, plus minus the square root of minus 5 squared, 25, minus 4 times 1 times minus 8. That's plus 32, all over 2 times A, which is 2. So these are the A values. So A1 will make it the evaluation where the root is positive. So we get 5 plus the square root of 25 plus 32, that's 57 over 2. My calculator tells me the first one is 6.27 to 2 decimal places. And then the second one, which we will call A2, is the one where the root has the negative symbol in front of it, minus, and that is minus 1.27 to 2 decimal places. So we've got these two A values. Now we know that B is 4 over A, so we can plug these in to find the equivalent B's. So B1 is going to be 4 over 6.27, which is about 0.64 to 2 decimal places. And then B2 is going to be 4 over minus 1.27, which the calculator tells me is about minus 3.15 to 2 decimal places. So this is our first solution, and this is our second solution. Now, again, when you're doing a question like this, you do want to check it. So you want to take those numbers, plug them back into the original expressions and see that the pairs of numbers actually satisfy these equations. As was the case with the last one, I've computationally checked these before the video. So I know that these are definitely the correct solutions. If you're doing equations like this and the forms are quite hard, the numeric forms are quite hard to write them, you can round them, right? And the rounding is fine, especially if the question tells you that that's okay. Often if they're very hard, it will tell you. One other thing we did in this question, when we used our B equals 4A formula, We plugged in the A that was 2 decimal place rounded. Now that builds in rounding error to the B value. But in the context of the HSC Maths curriculums, usually that's going to be fine. Right? If you wanted to be more precise, when you do B equals 4 over A, put the exact A expression in, and then you'll get slight more precision. But for the 2 decimal place roundings, this is pretty much perfect, and that's all we need.